Another tutorial on complex numbers. This is the fifth and last tutorial on complex numbers for the Edexcel Further Pure 1 course. Looking at the specification, I think we've done everything that we need to, apart from we need to define a complex number in the form r cos theta plus ir sin theta, and to do that we need to understand the terms modulus and argument. So we're going to tie off the loose ends here. Lastly, we're going to find out about a useful result, that the modulus of two complex numbers multiplied together is the modulus of the first times the modulus of the second. We're told by the examiner we don't need to know the argument law, so forget about that. Okay, let's work through. Let's start off by considering, by introducing the modulus and argument of a complex number. So just to get the idea across, say I have the complex number 3 plus 4i. This here is my complex number z, which is 3 plus 4i. Okay, now one way of thinking of this is to say, well, to find that complex number in the Argand diagram, I go across 3 and I go up 4. So any point in the Argand diagram can be found, any complex number can be found by telling you how far to go across and how far to go up or down. Okay, but another way, and it turns out to be a more useful way later on, is to instead tell you how far you are, straight line distance from the centre, and we call this the modulus of z. We talk about the size of the complex number, or we call it r. So we call this the modulus of z. So instead of telling someone to go across 3 up 4, we could tell someone to walk a distance, or we could say go a distance of modulus of z or r. But that's not enough, because we need to know what direction to go. So we need to be able to be told an angle, and we usually call this the argument of z, and we denote it theta. So we call this the argument of z. So because not only do we need to be told how far to go, we need to be told in what direction to go. So these are the ideas here, that the modulus is how far we need to go from the centre in the straight line, and the argument is what angle we need to go in, the angle we make with the x-axis. Now, how could we find those in this example here? Well, what we could do, we could say that the modulus of z, which is r, well, that is the hypotenuse of a right angle triangle, which has sides 3 and 4. So if I want to find out this length, it's simply 3 squared plus 4 squared square rooted, and we get 5. So the modulus of z, or r, in this case would be 5. How do we find the angle? Well, again, we've got a right angle triangle, we've got the opposite, we've got the adjacent. We could use trigonometry, and we could say that tan of that angle must be equal to opposite divided by adjacent, so 4 divided by 3. So therefore this angle must be the inverse tan of 4 over 3. And we call this the argument of z. Now we could work it out in our calculator. Our calculator should be in radians mode for this. We get 0.927 radians. Okay, so the argument of z in this example, or theta, is 0.927 radians, and the modulus is 5. So equivalent to saying to someone, to get to this complex number across 3 up 4, we could say go 5 units at an angle of 0.927 radians with the x-axis. So that's where the ideas come from. Okay, let's formalize it in general. So we have a complex number x plus iy. What that means, from our previous knowledge, is we've explained what that means by saying you go x across and you go y up. Okay, but now we want to instead of saying how far across and up or down to go, we say how far do you have to go directly from the origin, and we call this the modulus of z or r, and it's the straight line distance from the origin to there. So, in general, for this one here, the modulus of z, which we call r, is going to always be the square root of x squared plus y squared. Okay? And this is called the modulus of z. The other thing we need to know is the direction to move in, the angle that we make with the x-axis. Okay? And in order to find this, we use our right angle triangle trigonometry here, and we say that tan theta would be equal to y over x. So theta would be the inverse tan of y over x. And theta is known as the argument of our complex number z. The argument of z. Okay, now a couple of key things here just to fill in the finer details. R is always going to be a positive number. It is a length. We're going to think of it as a length. So in this case, R will always be bigger than or equal to 0. Now, how do we measure an angle with the x-axis? Well, what we say is that the angle can be anywhere. This is 0 here. This is where theta is 0. This is where theta is 90 degrees. This is where theta is 180. Here we could keep going and say that's 270 and 360. We don't tend to do that. We say instead we count this way up to 180, and then we count this way to negative 180. So this would actually be negative 90, and this would be negative 180 as well. That's convention. So our theta is always some angle that we make with the x-axis, but that theta we write down is got to be between 180, it's got to be strictly bigger than negative 180, and it has to be less than or equal to 180 degrees. That's in degrees, or if we're using radians, that would be pi, and that would be negative pi. So it's important how we define our argument. Our argument is always an angle made with the x-axis, but that angle has to be bigger than negative 180 and less than or equal to 180. The reason it can't be equal to negative 180 is because we've already defined theta as 180 there, because it can be less than or equal to. So going round this way, we better stop before we get to negative 180, otherwise we'd have two theta values meaning the same thing. Okay, so this is the general how to find the modulus and argument of a complex number. The modulus is we square how far across it goes, square how far up or down it goes, and we square root. It's the size of the complex number, the length of the complex number, and to get the argument is the angle that the complex number makes with the x-axis. We use a trigonometry to find that out, and we make sure our angle is between is bigger than negative 180 or less than or equal to 180 degrees, or negative pi to pi if we're dealing with radians, and we usually do deal with radians in FP1, so this is more useful. Okay, let's do a few examples. Here's an example. It says find to 2 decimal places the modulus and argument in radians of z is 2 plus 7i. You must always draw a picture for these, otherwise you'll go wrong when you're trying to work out your angle in particular. So always sketch a picture. Don't worry about the scale. I'm not going to have the scale exactly right. So we want 2 plus 7i. I'm just going to stick 2 here. It doesn't matter where 2 is here. That's 2. Let's just say that's z is 2 plus 7i. I'm not trying to draw it to scale here. These aren't units, okay? Now, how do we find the modulus of z or r? Well, we have got ourselves a right angle triangle here with sides 2 across and 7 up. So in order to find the modulus of z or r, it's going to be equal to the square root of 2 squared plus 7 squared. okay, and therefore it's going to be equal to the square root of 53, which if we do it to 2 decimal places, it's going to be 7.28 units. Okay, so the modulus of z or r is 7.28. What's the argument? Well, let's find, this is the angle we're looking for here. Theta is going to be the inverse tan, okay, of, that's 7 and that's supposed to be 2, the inverse tan of opposite divided by adjacent, so 7 over 2. We type that in our calculator. Our calculator in radians mode. Make sure your calculator is in radians mode. So if we type the inverse tan of 3.5, and we get ourselves that theta is equal to 1.29 radians to 2 decimal places. So our argument of z, which is theta, is 1.29 radians. And here we found the modulus. Here, underline your answer. We have found the argument. And we're done. Okay, I'm going to do several examples of these. You can pause the video and have a go at these because they're all quite similar, but I'm showing you different examples just to highlight to you in particular some complexities at finding the argument. But if you feel like you could go on and do it, do pause the video and try. Otherwise, just watch me going through. I'll give you a chance to do a few at the end on your own. Here's a new complex number, -5 plus 2i. Let's find that on here. It's -5 and 2i. Let's do this one to scale just to make it a bit easier. So this here is our z is -5 plus 2i. Okay, so there we go. Now the question is, how do we find the size of that line, which is we call the modulus of z or r? Now remember, here's a right angle triangle. This here is size 5, length 5, and this here is length 2. So the modulus of z, which is r, is going to be the square root of 5 squared plus 2 squared. Now let's not worry that this is -5, it doesn't matter. We're just dealing with a triangle here. Forget it's over this side. We're just dealing with this triangle that has a length 5 and has a width 5 and a height 2. So r is therefore the square root of 25 plus 4, which is 29. And if we're doing it to 2 decimal places, tap that in our calculator, the square root of 29 is going to be equal to 5.39. So this would be 5.39 units. So the modulus of z, or r, is equal to 5.39. That's our first answer. Now, what angle does this make with the x-axis, this positive x-axis here? So this is really why I wanted to show you this. I want to find this angle here. It's the angle made with the positive real axis. Okay, the positive x real axis. So that's the angle I'm looking for. Okay, now in order to find that, what we can do, we can find this angle here, which I might call alpha, and then I can subtract it from 180 or pi radians to find what this whole angle is here. So what we can do is we can say that tan of alpha is opposite over adjacent is 2/5, so alpha must be the inverse tan of 2/5. Keeping your calculator in radians mode, inverse tan of 2/5, you should get 0.38 radians. But if we want to find this angle here, we know that 180 degrees is the same as pi, so to find theta we would do pi subtract 0.38 radians, and we would get ourselves 2.76 radians. So the argument of z here, which is theta, is 2.76 radians. And that is our argument form. So you can see why it's very important to draw the picture here. Otherwise, we'd have forgotten that the angle we found is not the angle we're looking for, we have to subtract that from 180, or pi in this case. Okay, again, you can pause the video for the next one if you feel confident, otherwise watch me and copy this down. Here's another example, the modulus and argument of this complex number here. Let's draw it. -4, -1, something like here. So z is -4 subtract 1. Okay, we are trying to find its modulus, so that distance there, and we're trying to find the angle it makes with the positive x-axis. Now I can't find this angle because that's past 180 or pi. So this time I'm trying to find this angle here, theta, to describe it, and it will be negative. To do that, I'll find this angle alpha and then subtract it from 180. Okay, so here we've got a triangle, that's 1 and that's 4. So simply the modulus, which is easy, the modulus of z, which we call r, is going to be the square root of 1 squared plus 4 squared, which is going to be the square root of 17, which is going to be equal to 4.12 to 2 dp. And we're done in that instance. Okay, and next thing, we're going to try and work out the argument. Well, let's work out that angle first. We know that tan of alpha must be opposite divided by adjacent, which should be a quarter. So alpha must be equal to the inverse tan of 0.25, which our calculator in radians mode would be 0.2449, etc. But we don't want that, we want this angle here. So to get alpha, firstly we do a bit of side working. We need to subtract this from 180 to find out this angle here. So this angle would be pi subtract 0.249, which, typing that in your calculator, you get 2.8, you get 2.90 radians. Now the thing about this angle here is it's actually negative. So when I was working out theta, it's the negative of this because it's below the axis. We're going that way, so it's not a positive number, it's negative. So theta is negative 2.90, and that's called the argument. It's negative because it's going in that direction. Okay, and there we go. That is that one done. So go another one. Let's find the modulus and argument of this. 3 subtract 7i. So we go across 3 and we go up 7i. So this is 3 minus 7i. Sorry, mistake there. 3 subtract 7i. So 3 subtract 7i is down here. 3 subtract 7i. That's our z. We want to find the modulus of that here. And we've got ourselves a right angled triangle here. We're going to care about this angle. This is going to be the angle we care about. This here is going to be the modulus of z or r, this length here. So the modulus of z, which is equal to r, is going to be equal to, well, this is 3 and that's 7. So it's going to be the square root of 3 squared plus 7 squared, which, if we do a bit of working, the square root of 9 plus 49 is the square root of 58, which is 7.62. So the modulus of z or r is equal to that. And to find the argument, there's no subtracting from 180. We just want this angle here, and it's quite simple. So we know that tan of that angle is equal to opposite divided by adjacent is 7/3. So that angle is equal to the inverse tan of 7/3, which is 1.17. 1.17. So therefore the argument of z, which is theta, is not 1.17 but it's negative 1.17 because it's going that way, is negative 1.17 radians, and we're done. Okay, and at this stage now I'd encourage you to practice a few. I've got a few questions up here for you. For each one, draw a diagram, find the modulus and argument. Off you go. And the answers for these are as follows. So you should have got those answers there. Do check you can get those, it's very important. Okay, now just to finish off, we're going to use these modulus and arguments that we've just calculated. We're going to write a complex number in a new form. Okay, so we're going to finish off by using these. Now, the key idea here is on this slide, so do copy this slide as I go. Here's a general complex number, x plus iy. Okay, and that means your x across and y up. Our new way of talking about that is we can say, well, instead of describing it like that, I can say how far to go from the origin and in what direction from the x-axis. What angle do I make with the x-axis? Now, if I do have this r and this theta, if I know those, can I work out x in terms of r and theta? Well, using trigonometry, x must be r cos theta, and y must be equal to r sine theta, using basic trigonometry. So on the one hand, we know that z is x plus iy. Okay? But we know that x is r cos theta, so this must be r cos theta. And we know that y is r sine theta, so we could write plus I r sine theta. And this is still z. So that's a different way of writing z. We could factorize out the r, so take out the r is a factor of both, and we would have z is equal to r brackets cos theta plus I sine theta. And this is known as the modulus argument form of a complex number, and I've written it in the box here. The modulus argument form of a complex number z is x plus iy is of the following. Z equals r brackets cos theta plus ir sine theta. R must be positive and r must be a real number, and theta must be between pi and minus pi. It's bigger than negative pi and less than or equal to pi. In terms of degrees, if that was degrees, we would write it like this. Okay, so that comes from some basic trigonometry here. Knowing r and theta, how far across are we going? Well, r cos theta. How far up are we going? R sine theta. And we get ourselves a new way of writing a complex number. It turns out this way is very useful when doing some later work with complex numbers. So it's important we understand how to work out the modulus and argument form. Okay, to start with, you've just done these 4 questions. You've worked out the modulus and argument. So I encourage you, just write each of these 4 in modulus and argument form to start with. Here you go. Modulus and argument, you had done that in the previous work. So all it was a case of substituting into the modulus argument form z equals r cos theta plus I r sine theta. All you had to do was substitute the modulus in for r and substitute the argument in for theta. And these should have been the way you had written them. It was just a simple case of substitution. Okay, so in a normal question you might be asked to write that in modulus and argument form. Find r, find the argument by drawing the graph, by drawing the Argand diagram, and find those 2 numbers and then substitute into the form z equals r cos theta plus ir sine theta. Okay, I'm going to do a few more difficult examples because that's quite straightforward. So I'm going to start off with quite a tricky example. Now, it asks us to express this in modulus argument form, and it says give r and theta to 2dp if needed. Now, in order to do this, for a complex number, for us to be able to put it easily into modulus argument form and to draw it in the Argand diagram, because we're going to need to sketch these to get our arguments right, we need it in the form x plus iy, something like that. Now currently the complex part is dividing, so we need to make work this division out, kind of like rationalizing with thirds by multiplying top and bottom by the complex conjugate. 1 minus I root 3 over 1 minus I root 3. If we do that, on top we would get 3 1 minus I root 3, and on the bottom we would get ourselves 4. Okay, so this is equal to 3/4 minus root 3 over 4I. Okay, and that is in the form x plus iy. X is 3/4, y is negative 3 root 3 over 4. Now, I need to work out the modulus and argument of this complex number. To do that, always sketch yourself an argand diagram, otherwise you'll go wrong. We're going 3/4 across, so we're going 3/4 across, and we're going 3 root 3 over 4 down. Okay, so it doesn't really matter what it looks like, but let's just call that 3 root 3 over 4. We want to find ourselves r, we want to find ourselves theta. How do we work out r? Well, r is easy. R is that squared plus that squared all square rooted. So r is the square root of 3/4 squared plus 3 root 3 over 4 squared. Tap that in your calculator, and with a bit of luck you should get the answer 3 over 2. So you should get the answer 3 over 2 for that one there. How do I work out theta? Well, first of all, I could say that tan theta must be equal to the opposite divided by the adjacent. So tan theta must be 3 root 3 over 4 divided by 3 over 4, which is 3 root 3 over 4 times 4 over 3, changing that to a multiply and flipping the fraction. So that would end us cancelling that and cancelling that, cancelling that and cancelling that. If we take the inverse tan, therefore theta must be the inverse tan of root 3. Tap that in your calculator with your calculator in radians mode, and you will get yourself the answer pi by 3. But theta is negative here because we're going in that direction, so theta must be negative pi over 3. Okay, right, that's r, so therefore I can rub this out in a second. You keep this working. R is 3 over 2 and theta is negative pi over 3. So I'm just going to rub this out for now, this working. You'd have kept it in the exam. I just want to finish off by writing it in the correct form. Therefore, Z must be 3 over 2 cos of negative pi by 3 plus I sine of negative pi over 3. Okay, and that is your complex number now in modulus and argument form. Now I'm going to give you one to try yourself below, and I'm just going to show you the answer for this. So this one I want you to have a go at yourself. Very similar. Write that in r cos theta plus ir sin theta form in 10 seconds. I'll show you the answer. Okay, here's the answer. With a bit of luck, you got that, and these were given in radians to 2 decimal places. Okay, how about going the other way? If we were given the modulus argument form, how would we get the normal form, the a plus ib or x plus iy form? Well, all you do is you would work this out. You would work out on your calculator 3 root 2 cos pi by 4. Okay, plus I, and this would be 3 root 2 sine pi by 4. So tap this into your calculator and it will give you your A. So if you type in your calculator 3 root 2 multiplied by cos pi by 4, you get yourself 3. And I, what would this be? So 3 root 2 multiplied by sine of pi by 4. And you would get another 3. So it would be 3 plus I3, or the way you'd write that is 3 plus 3i. So A in this case is 3, and B in this case is also 3. And that's that. So I'd encourage you to have a go at one here yourself. Convert the modulus argument form into the normal a plus ib form. When you did that, with a bit of luck, you got the following. You got negative 3 root 2 for your a and 3 root 2 for your b. Okay, and let's continue. Last thing I want to talk about is a special result. Now, it turns out, I'm not going to show you this, but if you multiply two complex numbers together and work out the modulus of that result, it's the same thing as taking the modulus of the first complex number and multiplying it by the modulus of the second. Okay, so we're going to check this is true in a few examples, and I'll leave you to check this is true in a few examples. You should be aware of this result and be able to use it. If someone asked you what the modulus of z1 times z2 is, rather than multiplying z1, z2 and working out the modulus, it would be easier if you knew the modulus of z1 and z2 to multiply those. So let's just have a look at that here. Here are two complex numbers. Find the modulus of z in each case. Well, the modulus of z1 is the square root of 3 squared plus 4 squared, which is going to be equal to 5. The modulus of z2 is going to be the square root of 4 squared plus 3 squared, which is going to be equal to 5. And what would z1 times z2 have been? z1 times z2 would have been 3 plus 4i multiplied by 4 minus 3i. If we had actually worked that out, 3 times 4 would give me 12, 3 times negative 3i would give me negative 9i, 4i times 4 would have given me plus 16i, and 4i times negative 3i would have given me plus 12. So I would have got for this 24, and I would have got for this plus 7i. So what's the modulus of z1 times z2 then? Well, it's going to be equal to 24 squared plus 7 squared, the square root of that. And we get 25. And the modulus of z1 times the modulus of z2 is 5 times 5, which is 25. So it worked in this particular case here. Okay, so this result we were able to verify and check it. I'd encourage you to do the same in this particular example here. Work out the modulus of z1, the modulus of z2, find z1 times z2, and check that the modulus of z1 times z2 is the same thing as this modulus times that modulus. Okay, and off you go. Okay, and showing you the answer for that, the modulus of z1 was root 5, the modulus of z2 was 2 root 5, the modulus of z1 times the modulus of z2 would therefore have been 2 times 5, which was 10, and the modulus of this thing is 10 as well. So we got the same answer. And that is all for complex numbers. Now, I would encourage you though, just to tidy up your knowledge, read chapter 1, page 14 to 21, work through those examples and do everything in exercise 1F on page 14. Thank you for watching. I hope you found the video useful in your studies.